Welcome. Today we will dive into deep belief networks. A DBN is a powerful type of deep neural network that learns to transform raw, unstructured input into intelligent, categorized output. The core building blocks are restricted Boltzmann machines. Multiple RBMs are stacked on top of each other. Each one serves as a layer in the pre-training phase. During this pre-training phase, the network learns layer by layer using unsupervised learning. It minimizes an energy function to discover essential features in the data without needing any labels. Once pre-training is complete, a final supervised layer is added. We perform fine-tuning via backpropagation using labeled data to dial in the final predictions. Let us look closer at unsupervised pre-training. Pre-training gives the network a massive head start. It initializes the weights in a smart data-driven way before any supervised learning begins. By feeding in unlabeled raw data, the stacked RBMs discover hidden features on their own. They reconstruct the input over and over, slowly learning the structure. One of the most fascinating aspects of a deep belief network is that it is a generative model. This means it can generate brand new data. By understanding the joint probability of visible and hidden units, we can sample the network to dream up new outputs. Information flows bidirectionally. It flows up during recognition to classify an image, and it flows down during generation to hallucinate new data. As data moves up the network, it forms a feature hierarchy. Each deeper layer learns increasingly abstract representations, built directly on top of the simpler features extracted by the previous layer. At the bottom, it detects basic edges and dots. In the middle, it combines those into shapes. At the very top, it recognizes full complex objects. This brings us to a breakthrough concept introduced by Geoffrey Hinton in 2006, greedy layer-wise pre-training. This was the key that made deep networks trainable in the first place. The process is elegant. We train one layer at a time. After RBM layer 1 is trained on raw input, its hidden activations become the input for RBM layer 2. This local optimization happens greedily, layer by successive layer. But how does a single RBM actually learn? It uses an algorithm called contrastive divergence. It works in two phases. In the positive phase, reality, or the raw input, flows up to compute hidden activations. In the negative phase, the network reconstructs what it thinks it saw, flowing downwards into fantasy. We compare reality to fantasy, and update the weights to chisel away the difference. By repeating this process, the network's energy rapidly decreases, and it becomes exceptionally good at modeling the underlying probability distribution of the data.